topic, I would just like to share these data that you are maybe aware of. What are the differences between different materials of silicon carbide, and gallium nitride? For sure, looking to the table at this slide, we can conclude that silicon carbide and GaN are for sure technologies with better performance than silicon, and as a consequence, there are different benefits that we can have in devices itself, and of course at the end application which they are targeting. More details will come from other speakers today, but here maybe slide is good for the reference, and also it is good to see later on that each application has definitely a technology of choice which is bringing benefits. So it's not necessary that the best technology is giving the best fit for given applications. We will see this later on during the webinar. Having said this, there is a question: in which application the best fit is GaN, silicon carbide, or silicon? And here there is a famous graph that can maybe give a hint in which direction to think. For sure, gallium nitride is reserved for very high switching frequencies. Then still we have IGBTs that are leaders in a low switching frequency, very high power equipment. And then silicon carbide, which is targeting very high power and high switching frequencies. For sure, silicon carbide is there to compete with superjunction and GaN in lower power range. And here there definitely specific requirements of applications will prevail in a component, in choosing the right technology. So on the other hand, we can see at the market that gallium nitride and silicon carbide is picking up. So more and more products are developed in these technologies. Silicon carbide for sure is led by automotive, gallium nitride for the moment by consumer, but we see definitely in industrial applications more and more new designs with wide bandgap technologies. And at this moment I would like to hand over presentation to my colleagues from Infineon. And as said before, we will hear some interesting examples of applications with silicon carbide and gallium nitride, and especially, I would say, focus on gallium nitride in motor drives.
Thank you very much for the introduction, Milan. So he's given some basic comparisons of the material properties, but what I'd like to do in this next section is dig a bit deeper. Not just the materials, but the transistors themselves. What are the differences between these three types of switches, so that this will inform the next section from Martin on some examples of when to use silicon carbide, or GaN power transistors. So I always like to start by showing this spider chart. It's essentially the same data that Milan was showing before, because it really indicates that there are material benefits if we were to make the same exact transistor, the same exact MOSFET or IGBT or BJT with silicon carbide, and GaN. But that's not the reality, because for silicon, there's a wealth of different devices that you could choose. JFETs, thyristors, planar or trench MOSFETs, superjunction MOSFETs, IGBTs. For silicon carbide, we essentially are just looking at planar or trench vertical MOSFETs, whereas for GaN, things change quite a bit. The market is full of these so-called HEMTs, these lateral power devices, different configurations, but always this lateral type of HEMT. So in the same way that there are different characteristics of a thyristor and a MOSFET, there are differences between these different devices beyond just the material properties. So let's look a bit at why we have different types of transistors for these different semiconductor materials. The first thing you have to understand is that silicon is grown from a seed crystal into these very long ingots. They're about 2 meters long and up to 30 centimeters, so 12 inches in diameter. They're grown very fast. It's a very mature technology. If you remember back from your university days, usually this is compared to making candlesticks, where you dip the string into the wax and you rotate the string, and gradually this molten silicon layers upon itself, and you have this very high quality intrinsic silicon wafer, or doped N+ silicon wafer, or ingot, which is then sliced into wafers. Now, silicon carbide's a bit trickier because silicon and carbon have different melting temperatures. So you can liquefy molten silicon carbide bath, but we don't want to grow the wafers from this liquid because they will separate due to the different melting temperatures. So instead, this liquid is vaporized and the crystal structure is grown as what's called a boule, informally called a hockey puck. Looks a bit like a hockey puck, hence the name. At the top of the crucible, you can see this lime green color here above the yellow liquid silicon carbide. So that boule is then sliced, and then we again have wafers. So we have silicon or silicon carbide wafers. What do we do with those wafers? Well, we make a vertical power device. Let's talk about a MOSFET to start with. It's just a simple planar vertical MOSFET. We start with that N+ wafer, which was grown as an ingot or a boule. We use homoepitaxy. So again, this vapor-based deposition of another material, but it's the same actual material. It's just N- doped instead of N+ doped. A very thin layer of that to create the drift region. Then we do some ion implantation, not adding any material, just changing the material that's N- epi to become P-type or N+ type. Then we apply some oxidation steps to create the oxide for the MOS capacitor, and then we add the gate, source, and drain metal. Now notice a couple things here. One is that we have gate and source at the top of the chip, or the top of the wafer where this is grown, and then drain at the bottom. The other thing is that if we're talking about a silicon power MOSFET here, this is silicon from end to end. Everything other than the metal is silicon. We have N+, N-, P-type silicon. We have silicon oxide. These are all homogeneous. Silicon carbide would be the same. Everything on here is silicon carbide. So if we wanted to make a GaN MOSFET, we would need a GaN wafer. Here's why that's a little bit tricky. So silicon, as I just said, grows quite quickly in the range of millimeters per minute. You need about 1420 degrees Celsius to grow this from liquid. Silicon carbide, now it's millimeters per hour instead of minute. That's a bit slower. Also, much higher temperature is needed. So you end up with a much smaller hockey puck boule here, as I said. For GaN, it's much more difficult. In order to keep the gallium and nitride from separating, you actually have to flood this chamber with pressurized ammonia. It's a very corrosive environment. The chamber is very heavily engineered to be able to survive that. The growth rates are very slow, in the range of millimeters per week. So while there are bulk GaN wafers available for purchase on the open market, they are very costly, typically very small in diameter, and the quality level of impurities is not on par with silicon or silicon carbide. So that means we don't have commercially ready GaN wafers from which to grow a vertical GaN MOSFET. Luckily, we don't need that because GaN is a piezoelectric material, which means that if we implant GaN on a foreign substrate, typically we use silicon, but people could grow a thin layer of GaN on top of silicon carbide or sapphire, a lot of different materials. We typically use silicon because it's readily available and cheap. You grow some GaN on there, heteroepitaxy, and then you grow some AlGaN, aluminum gallium nitride. Now, at the exact boundary between these two materials, there's a piezoelectric effect that creates a channel, a highly mobile channel, very much like a MOSFET channel, but it's lateral. And because it's a wide bandgap material, we can block the voltage laterally. So we have a lateral transistor where the voltage is blocked along the top of the chip, top of the wafer, and the current is conducted there. So the silicon or silicon carbide or sapphire substrate that we started with, I like to say it's like a dinner plate. It's just holding up the active area. It's not doing anything electrically. So we have these three different types of devices. We have silicon MOSFETs, could be planar, trench, or superjunction. We have silicon carbide vertical MOSFETs, and we have these lateral HEMTs. But the real question is, how do the devices, the actual transistors we can buy, compare? Well, for one thing, we have to be prepared that the differences are more than just gray areas. Sometimes there are white and black differences. So for example, reverse recovery. A superjunction silicon MOSFET like CoolMOS has quite a high QRR. Silicon carbide, because it's not superjunction, is much lower. So less than a tenth of what the QRR is for CoolMOS. Now, reverse recovery adds a lot of switching loss, a lot of EMI, a lot of heat. Because a GaN transistor has no PN junctions, no minority carriers, it has no QRR by definition. So that's a huge advantage. It's not a shade of gray. This is white and black. But there are other things that are more gray areas. So here what I'm going to do is walk through some characteristics of data sheets for devices that are all in the same toll package. They're all 650 volts rated. They're all about 50 milliohms, typical at room temp. The first thing we can notice is the junction capacitances are quite different. They're highly nonlinear with respect to voltage for the silicon superjunction. You especially see many orders of magnitude, over 1,000 times dropping for CoolMOS in the low voltage range. This is because before you can deplete the drift region vertically, you have to deplete this area between these deep wells. And then once you get past these wells, you deplete vertically. Now, silicon carbide trench MOSFETs are similar in that there are some wells, so you have to deplete the regions between the wells first, and then you deplete vertically. There's a little bit of nonlinearity. And again, there's completely different geometry. So for CRSS, notably, there's a bit of a drop-off, but for CISS and COSS, it's pretty flat with respect to voltage compared to these other two. So the shape is different. I would say more linear, more flat with respect to voltage, moving left to right, but also the values are much lower. The capacitances are much lower. I find that it's much more insightful to look, instead of the capacitances, to look at the charges and the energy loss. So now let's look at EOSS and QOSS. Now, EOSS, which is this cyan-colored plot on the same y-axis, is not that different between the three technologies because it doesn't reflect that high charge value in the low voltage range. However, if you're doing hard switching in a motor drive or in a totem pole PFC, any kind of symmetric half bridge, your hard switching losses are far more related to your QOSS. And likewise, if you're doing a resonant design like LLC, it's QOSS that dictates the dead time need for resonant switching. So it's really this magenta line that is more meaningful. And this is much, much lower, going from silicon superjunction to silicon carbide because of the lack of those deep wells that have a lot of minority charge. So that now the QSS is much lower for silicon carbide, and it's still lower again for GaN. Only a little bit lower, but you have to consider that this doesn't include your QRR, your reverse recovery. So if we consider the reverse recovery and the QSS as dominating your switching loss, silicon carbide is still quite a lot higher than GaN in terms of hard switching. Now let's look again on the same axis, X and Y axis, at the QG. So every time you turn on the gate of your transistor, you're going to be losing an energy equal to the area above the curve here, this blue shaded area. And then every time you turn off that gate, you're losing the energy below it. So it's really this rectangular area that you're losing for every switching cycle of that gate. You can see that area is quite a bit less for silicon carbide, about half. But then it's an order of magnitude, again, smaller for GaN. So we've saved a lot on the hard switching loss or the resonant dead time requirement. And now we've saved a lot on the gate driving loss. And the smaller gate charge also allows us have very snappy transitions, on and off, very high BVDT if you so choose. The area where silicon carbide really shines is high temperature operation. The temperature coefficients of conductivity of GaN and silicon are quite similar. So if you look on the left and on the right, the RDS(on) over temperature is nearly the same for a comparable silicon superjunction MOSFET and a GaN HEMT. But silicon carbide is much shallower because of the physics of silicon carbide and the MOSFETs we make from this. So most devices will have this very flat RDS(on) over temperature. So this all comes to the conclusion that silicon is still a great technology, mainly because it's a very mature technology with the lowest cost, whereas silicon carbide has a huge advantage in high temperature performance. It also has advantages in switching performance compared to silicon, but by far, all of the figures of merit, the reverse recovery, QSS, QG, they point to GaN being the best option for switching loss, switching performance, high switching frequency. So with that in mind, I'd like to hand over now to my colleague, Martin, who will talk about how we can leverage those benefits in some applications.
Hi, this is Martin. So my topic would like to share is how to use this film material to design the power supply, so from low power to high power, and what is our selection. So let us go to talking about the low power. So this is a 240 watt USB PD. And the topology is a traditional feedback, traditional boost converter, and then with the hybrid feedback. And in here, because the PD requirement is high power density, and with also certain efficiency requirement, so you can see that the left-hand side, we have a simplified circuit diagram, which is using our silicon device to replace the bridge rectifier, the second device in the PFC, and then gallium nitride device for the hybrid feedback, and then silicon device again in the synchronization rectifier. And we provide 240 watt output, which is meaning that we have a wide range output voltage from 5 volt going up to 48 volt at the output current is V on, and also the 5 ampere current. That is the short table, a summary table for about our device usage. And let me explain more detail why we're using different device in different position of our USB PD design. So first of all is the active bridge in front of the PFC stage. So actually, obviously, that active bridge, we are only looking for very low RDS(on). Switching performance is not so important. So it means that we are interested in the RDS(on), and for sure with certain optimization in terms of power density. So select correct RDS(on) with the IDS and then also the package. Think about the thermal conduction losses. That is important, or that is critical criteria for this active bridge device. And also one important thing is because the bridge is in front of the EMI filters. I mean, it affects the EMI. So transient speed is making a little bit difference between the normal switches. We need to PT general transient speed, which means that we need to also consider very low output driving current driver IC or slow down our transient speed in our device. So suggestion is we can consider using our silicon MOSFET, high voltage silicon MOSFET as a active bridge device. And in the PFC stage, the working mode we call the quasi-resonant mode boost switch. So meaning that we have a similar as a DCM mode, which is a little bit hard switching. So we need to think about that, okay, so the turn-off losses. But it is better than traditional CCM boost because we have a QRM, so meaning that when the device turn off, we have a relatively low VDS voltage for turn-off situation. And it also variable switching frequency. And one important thing is also consider is the EMI, because in the PFC stage, actually the bulk cap is much bigger than the whole PFC stage. So meaning that increased switching frequency will not help too much. So a medium or relatively slow switching frequency should be selected in the PFC stage. So that's why we also select the silicon device. But in this selection, we have a select better, less hard switching losses series, which is a CUMA C7 or CMA. Is a better fit for our QRM boost switch. In the DC-DC stage, we select the hybrid feedback. Idea for the hybrid feedback is provide wide range output voltage, and then you can see we don't need any additional buck converter at the output side to fulfill the low output voltage. So actually, the hybrid feedback switching performance is, first of all, is a variable switching frequency converter. It's achieve a zero voltage switching. It's a continuous resonant mode. So meaning that the device can achieve zero voltage switching at the primary side and then zero current switching at the secondary side. So operation pretty similar as LLC. So and you can see that, so because this is wide range output voltage, and then the operation is a variable switching frequency. So that's why you need to consider about the driving losses is one of the critical, particularly at the low power application. So zero voltage switching, we can achieve a very low switching losses, but driving losses we cannot avoid. We need to drive our device. So low driving losses meaning that GaN is one of a good option. So that's why we could recommend also the gallium nitride device in our hybrid feedback primary side. And also because the under certain abnormal cases condition, so we need a good robust body diode with the low driving losses. So this is also one of the reasons GaN is selected in here. And then in the synchronization rectifier side, so we can select a Optimus, which is because we have a certain wide range output voltage. So you can imagine that we need to at least using at least around 100 volt or 80 volt Optimus device. And then Optimus is one of the good option, okay, when the voltage crosses below 100 volt. This is a optimized between performance and also the operation of the wide range output voltage. So let us move some medium power, looking for the high power density, very typical 3.3 kilowatt, like server power, telecom rectifier. How we select our device in a different stage. So in here, so you can see that we have a totem pole PFC stage, and then we have a small boost converter, and then we have a half bridge LLC converter. So you can see that in a different color, meaning that we are presenting a different material and technology device usage. So in here, so this is the in the PFC stage, we are using the totem pole. So in the totem pole, you may know that, so we have a fast leg, fast switching frequencies leg, and also the AC main leg. And in here, what we select or what we recommended is using silicon carbide MOS in the fast leg. It was because it's providing the good optimization. So first of all, wide bandgap provide very robust body diode, which is this topology looking for, particularly for CCM totem pole PFC. And also, the switching frequency in here compared with, as mentioned by our colleague Edward. So the switching losses, the lowest switching losses is gallium nitride. But in here, we are not switching too fast. Usually, due to some EMI concern, the designer usually design their switching frequency in this PFC stage is roughly around 65 kilohertz. Maybe some design is going up to 130 kilohertz. That is the limit. It was because the EMI requirement. And third is, even we try to increasing our switching frequency, yes, for sure we can reduce our inductor, our input inductor, but another component still keep PT or certain volume, for example, like our output capacitors and also our EMI filter. So that's why increase the switching frequency in the PFC stage, we need to consider some balance between the EMI and then the output cap for the whole uptime. So silicon carbide is one of is a good selection in the PFC totem pole. And in the fast leg, in the slow leg in here, so actually this is just focus on RDS on, no switching performance requirement. So that's why silicon device is one of the good option, okay, using in the slow leg. And in here, as I mentioned again, because in this design, what we want to do is the high density. So we understood that we have a lot of PFC output bulkhead, which is served for the whole uptime, not only for the ripple filtering and also for the whole uptime. That is the basic requirement for the server power or telecom. So we would like to minimize that capacitors value or the size of the volume of the cap. So that's why we put a small boost converter in the middle stage between PFC and then the DC-DC. And in here, because the boost converter is just operate when the whole uptime requirement. So meaning that AC main is disconnected and then we need to keep certain milliseconds to maintain the output power at the full load condition. So this boost converter is really small size and then the operation is really short time. So consideration only is how to make this small boost converter as small as possible. And the traditional small boost converter like using silicon, MOS, and then silicon carbide diode for the short-term boost up or to maintain the whole time only. So that's why silicon MOS and then silicon carbide diode is used in there. And the LLC, as mentioned again, so we are targeting for the high density. So LLC is a LLC with certain range output voltage. Then you need a certain variable switching frequency. And also we would like to reduce all those isolation transformer as well in here. So that's why we try to increase this half-pitch primary side LLC switching frequency going up to 400 kilohertz to 750 kilohertz in this range. So that's why you are looking for the really high switching frequency, low driving performance, and also in some cases, LLC, you need to avoid some hard computation conditions. So that's why gallium nitride device is a perfect fit in this stage, particularly in the primary side, and then to fulfill our requirement, our design requirement in the high frequency LLC half pitch. And again, silicon will be back to this as a synchronization rectifier. It was because you need to make the balancing between medium voltage gain and then silicon. So if the device below certain voltage, so we understood that silicon still have an advantage, or not only the advantage, and also design good performance for the synchronization rectifier applications. So let us move to more high power. So this is more high power, so only for the PFC stage, which is 11 kilowatt bidirectional operation. So what we are doing is we are mix our device. We are using our silicon carbide and also our silicon device to make this a 3-level active cam totem pole PFC. And in here, you can imagine that we have a lot of moderation to select that, okay, which portion or which part. For example, like in our moderation methodology, so our moderation scheme can allow us using relatively less wide bandgap device component. For example, in here, like our T2 and T3, so only this middle leg, only these two device, T2, T3, and also the leg space should be in the middle in here. And then to using silicon carbide, and meaning that the 11 kilowatt solution, we only using 6 pieces silicon carbide MOS to fulfill the bidirectional operation. And then the remaining device, this 12 pieces is using silicon to balancing between the total system cost. So this is a moderation scheme. So why T2, T3 is selected as a silicon carbide and the remains is the silicon? It was because the switching frequency. And you can see that the T1, T5, T6, and T4, they are AC main switching frequency. So meaning that we just focus on RDS on. Locus RDS on, better efficiency. And in T2, T3 actually is like the totem pole fast leg operation, which is a drive by the switching frequency, and maybe 65 kilohertz in here. And then you can see that we need to using silicon carbide MOS, which is because it's not only acting a switch and also acting as a diode in some cases. Okay, so that's why really robust body diode is must. And again, because why silicon carbide is selected rather than GaN, it was because 65 kilohertz switching frequency. So driving losses, switching losses, full balancing between design effort, that silicon carbide is more appropriate in this application. And also one advantage in silicon carbide in PFC stage is the higher temperature, meaning that you can using relatively low RDS on, let the TJ going up a little bit, and then to provide better system cost balance performance. So this is my application side. So, and in here, so we have a certain reference link. So just for your reference, and then all the demo board are existing in our Infineon homepage.
So following up on what Martin covered, I'll talk a bit about how GaN specifically makes a lot of sense in motor drive applications, which is a bit counterintuitive. Motor drives are typically fairly low frequency applications. Very often you'll see motor drives in the range of 8 kilohertz, 10, 12, at most 20 kilohertz. Meanwhile, for GaN, we're often talking about megahertz level switching. So the motivation to use GaN in motor drives is a bit more complex than it is in the applications that Martin covered. If we start with the properties, the characteristics of the GaN transistor, we have a lower RDS on in a given area. So if we have a specific package or board area available, we can have a lower RDS on, lower conduction loss. We have no reverse recovery. This is very empowering in a lot of ways. we have low QoSS, and also within that QoSS, the CoSS is very linear. We have the low QG, and the packages are typically pretty low inductance. So what we can do with that is lower switching loss. Now, this would be true even if we wanted to keep the switching waveforms at the same slew rate. If we wanted to have 5 volts per nanosecond, 10 or 20 volts per nanosecond, the switching losses will already be lower because of the lower QoSS and the lack of QRR. But because the CoSS is so linear, and because we don't have those minority carriers fighting against us, we can also make the switching waveforms very clean. And we find that very often these waveforms are so free of ringing and EMI that they enable designers to increase the dVdt quite a lot. And the inverse of dVdt, of course, is time. So this means if you have 400 volts or 48 volts and you need to switch that, you need to commutate that, you can do it in fewer nanoseconds and reduce your switching loss. You can also reduce your dead time to almost zero. We're talking about going from 1 microsecond to 50 nanoseconds, or going from 300 nanoseconds to 10 nanoseconds. So it's really improving your THD, your voltage utilization in terms of maximum speed. Now, all of these things are true if we don't change the frequency. However, we find that typically system designers using GaN do increase the switching frequency a little bit. They may go up by a factor of 2 or a factor of 10. It really depends. The reasons to go to higher frequency can be grouped into 3 main takeaways. There's the higher power density, higher efficiency, and better control. So the higher power density mainly comes from the reduction of bulk capacitance. We could be talking about eliminating electrolytic capacitors or film capacitors from your design entirely and using only ceramic caps. But you also get the benefit of the smaller power stage because of the smaller, the lower RDS on times area. Maybe you can reduce a 10 by 10 millimeter package to a 5 by 6 millimeter package and free up some area on your board. You can also get rid of the heat sink or use a smaller one because of the lower switching loss or the lower conduction loss if you prefer. The higher efficiency mainly comes from the benefit to the motor, which I'll get into in a bit later. This is not true for every application, but in many cases, we find that the higher frequency makes a motor run more efficiently, even if the inverter efficiency is not really affected. And then lastly is the control loop bandwidth. So this means that you can respond faster to physical events. Your dynamic response can be better. You can also shape your phase current waveform more precisely for better motor performance, better motor lifetime, more quiet operation. So let's do a deep dive and look at a very specific example. Let's look at a 100 volt silicon MOSFET, the best, the latest technology, our Optimos 6, using the 100 volt Optimos 6 with the same RDS on as our 100 volt first generation CoolGaN. Both of them about 2.6 milliohms. And the first thing you'll notice is that the QoSS is cut in half. The QRR is, of course, gone. The gate charge is reduced by a factor of 5. And then if you consider the gate driving energy, the driving voltage is also half. So this is a 10 times reduction in driving loss. Because of all those factors, if we are trying to switch with the highest dVdt, in this case, we're limited only by the ratings of the device. So we obviously can't let the drain voltage or the gate voltage ring beyond the datasheet limits. So if we optimize purely for switching performance, not worrying about EMI, then Optimos allows you to switch up to 200 kilohertz. But of course, you pay a price. You're increasing your loss across the full load range for every 10 kilohertz, 50 kilohertz that you increase the frequency. So in a motor drive application, it maybe doesn't make sense to go to this higher frequency because there is this penalty. With GaN, you kind of flip this logic on its head. The penalty is so low, it's basically negligible. So then the question is, why not go to higher frequency? There's really nothing holding you back. We can switch very easily at 100 or 200 kilohertz, and the full load power loss, the system efficiency is still lower than silicon would be at low frequency. However, it is worth noting that you usually don't want your waveform to look like this blue one here. And those efficiency curves I showed you in the previous waveform, all of them looked a bit like this blue waveform here, the silicon and the GaN. We were letting the drain voltage ring because then we get the highest efficiency. Now with a silicon or silicon carbide MOSFET, this ringing would have a lot to do with QRR, meaning that it's very difficult to make it go away. Whereas with GaN, we can make a very small change to the gate driving circuit. Here we're talking about maybe changing a 1 ohm gate resistor to a 3 ohm gate resistor. And the impact is profound. You have a relaxed slew rate, no overshoot, no ringing at all, a very clean, almost cartoonish waveform. It looks like it was just drawn with a pen, but this is an experimental result. Now, the consequence of slowing down the dVdt from 50 to 20 volts per nanosecond and getting rid of all of that ringing at 100 kilohertz is less than 1 watt at full load, less than 10% increase in your full load power loss. You know, this is pretty much in the weeds. So not only can you improve your efficiency and increase your frequency, but you can also tune EMI much more effectively in your design with GaN. So what I want to show you is an example of how this applies to the motor efficiency. This was an experiment that we ran a few years ago with an off-the-shelf motor used for agricultural, industrial, cargo type drones. So 1 kilowatt drone motors running at a 48 volt battery. We have one of our 100 volt GaN boards here running at 100 kilohertz, driving this motor across a 40 centimeter cable. Now, it just so happens that these types of motors, and quite a lot of motors out there, have fairly low phase-to-phase inductance in the range of 10 to 100 microhenries. And this is about the same range of an inductor that we would use in a DC-DC converter. So in the same way that higher frequency benefits the AC losses of a discrete inductor or transformer, they benefit the losses of the magnetics here, which are the motor. So going from 20 kilohertz to 100 kilohertz, we see an overall system efficiency benefit of about 7%. And this is most visible in the motor. So in the motor temperature, the windings and the core, they drop by about 13 degrees C across the full load range because we've gotten rid of all of this ringing, this current ripple in the phase current, which causes iron losses in the core of the motor. It also causes AC resistance losses in the windings. So by cleaning up that waveform, we improve the temperature and the efficiency of the motor, which improves the overall system efficiency. So just to demonstrate what this can mean in a practical application, if we're talking about a 1 kilowatt motor, so here, this top one at 48 volts, this could be for a humanoid robot, elbow or shoulder joint or a knee. Now on this one below, this is for 400 volts. This could be for something like a heat pump or an industrial machine running at 1 kilowatts. And we are able to take our GaN transistors, especially our integrated GaN transistors at 100 volts or 650 volts, pair them with the latest and greatest microcontroller called PSOC C3 and our latest current sensors and make a complete 1 kilowatt system solution in the size of a coin, which can very easily be integrated into the chassis of the motor so that you have no electronics outside of the motor housing. This really helps with the radiated EMI design. If any of you are attending PCIM next week, we will have these boards on display as well as we had them at APEC last month. So with that, I'd like to conclude. I most recently here just talked about GaN for motor drives, but really this is about how our CoolMOS, OptiMOS, CoolSiC, and CoolGaN all offer great advantages for power electronics. We have state-of-the-art topologies and system solutions that show how you can leverage all three semiconductor technologies in the same system or in different systems. You can partition lots of different ways to achieve the best size, performance, and cost. Now, GaN does bring some unique advantages to motor drives that the other technologies do not. But even for motor drives, there are cases where silicon or silicon carbide offer a clear advantage. There's let's say a right fit for all three. But this is a moving target. You have to be aware that a lot of this comes down to the technology improvements year over year. The improvements year over year for silicon MOSFETs are still pretty significant, but they are more incremental than they were 20 years ago. Meanwhile, silicon carbide is certainly newer, but GaN is the newest, meaning that we see the highest acceleration, the highest improvement year over year of GaN technology, and then next to that silicon carbide, and then third silicon. They're maturing at different rates, and this you can see this in these figures here in terms of the wafer sizes. We're producing silicon power transistors primarily on 12-inch 300 millimeter wafers. Silicon carbide is gradually transferring over in the industry from 6-inch to 8-inch wafers. Meanwhile, GaN is mostly on 8-inch already, and it's moving towards 12-inch because it's produced on silicon, so we can take advantage of those readily available 12-inch silicon wafers. So alongside these larger wafer sizes, we're seeing advancements in the figures of merit and cost positions. So really you have to stay tuned. The right fit for your system today may not be the right fit one or 2 years from now. So I would like to conclude by saying, let's work together to find the right fit for your next design. Please keep us in mind, Infineon and EBV, for your next design, whether you're interested in wide bandgap technologies or off-the-shelf conventional silicon MOSFETs.
All right. Well, thank you, Edward and Martin, for that excellent presentation. It's really fascinating to see so many new efficient power technologies that are enabled by the advancements in transistor technology that you just mentioned are moving ahead still rapidly after all these decades. So we already have several interesting questions, but I want to let our audience know that there's still time to submit your questions. Edward and Francesco, are you ready to answer some of these questions?
Yes,
of course.
Ready.
Hello, everyone.
All right, here we go. First question is a pretty broad one here. It's how does GaN technology improve motor performance, cooling requirements, and control dynamics?
Yeah, it's a good question. I covered a bit in the presentation just now. The control dynamics really comes down to the simple fact that you can't have a control loop in your motor control firmware that's at any higher frequency than the switching. So if you're switching at 20 kilohertz, then your control bandwidth can only be 20 kilohertz or less. But if you're switching at 100 kilohertz and you have enough horsepower in your controller and well-written firmware, then you could have up to 100 kilohertz of control bandwidth. So this means you can have a faster response, but it also means you can just have better shaping of the back EMF and the current waveform. And this can help with also the efficiency of the motor in the same way, which would reduce the cooling requirements of the motor.
Yeah, very good. Can you please comment on the GaN reliability at high current?
That's a very broad question. There aren't any GaN specific issues for reliability at high current. There's of course always a safe operating area. GaN and silicon carbide have quite different, let's say, transfer characteristics. So peak current capability, GaN, silicon, and silicon carbide all do, but we don't generally find that this causes much of an issue in terms of reliability.
Yeah, I wonder if some of that is just kind of the history of, you mentioned moving to higher, bigger wafer sizes, the tooling has gotten better, the processing has got better, and so the reliability and performance of these GaN and SiC devices has improved along with it. And some of the problems that you might have seen a decade or more ago really just aren't in the same scope today.
Mm-hmm.
Yeah. So let's see, this question is asking, thank you for the presentation. I'm also interested in drivers and high power amplifiers, 3 kilowatts for RF front ends. What is your recommendation in terms of best technology to use for those applications?
So I can take this question. So I think they ask about application RF power amplifiers. At Infineon, we have two possible technologies to address this application. One is based on silicon, and the other one also on GaN, the so-called RF GaN, of course, with the specific features for RF applications. I would say the selection criteria are similar to other applications. That means, of course, for very high power density, definitely GaN has a superior performance, but silicon is still, let's say, respectable in performance in this kind of application.
All right. Given the complexity of GaN manufacturing, I'm interested to know if such technology is manufactured within Infineon or outsourced.
So we produce all of our gallium nitride and our silicon carbide in-house. Now, we don't make the wafers. GaN is produced on silicon wafers. Silicon carbide is, of course, produced on silicon wafers. We do buy those wafers. It's a very, very mature, very competitive market out there. Lots of suppliers all over the world. But we do all the processing ourselves, actually here in Villach, Austria, where Francesco and I both live. But we do have other sites around the world that are being enabled to scale up with our GaN and our silicon carbide. We own all the technology, all the processes. It's all organically developed in-house, and we control the process from end to end.
Very good. What is the current limiting factor for medium power application switching frequency? Is it the current MOSFET devices or something else?
Well, I would say that the power device, the power switches are definitely relevant or critical components in order to increase the switching frequency. Of course, also the magnetic components have certain limitations, but I would say that if you use technologies like wide bandgap, you definitely enable higher switching frequency. And of course, you can reduce the size of the magnetics, considering that there are materials nowadays enabling also high switching, efficient high switching frequency operation also on magnetic components. And very important, we need to consider special construction for magnetic parts like transformer, also to minimize effect like proximity losses or skin effect on fringing flux, which of course kill the efficiency at high switching frequency.
Thank you for that detailed answer, Francesco. How do the body diodes compare between the three technologies? Do I need to place an anti-parallel diode on GaN for freewheeling like in an IGBT?
Yeah, this is a common misconception. So in silicon MOSFETs, silicon carbide MOSFETs, and GaN HEMTs, they all have a freewheeling mechanism. And that is literally a body diode in a silicon or silicon carbide MOSFET. In a GaN HEMT, it's not a literal diode. It's a mechanism of operation, or it's a mode of operation where the GaN HEMT will freewheel as a diode would. But the benefit is that a diode has minority carriers and reverse recovery. So all of that nasty QRR and ringing, this is because of the body diode. The GaN HEMT's freewheeling mechanism does not have a PN junction. So there is no minority carrier, no QR associated with it. But you do still get the complete benefit of the freewheeling mechanism. So you do not need to put an anti-parallel diode like you would with an IGBT.
Interesting. Thanks, Edward. In the hybrid flyback that you had on slide 21, why did you use GaN on the primary side instead of silicon carbide? Well, that's a very specific question.
And this is a fair question, because silicon carbide could be used definitely in the primary side. What makes the difference here is the very low QG of GaN compared to silicon carbide, which in this topology has an important impact on the efficiency. So it's mainly due to the significantly lower QG of GaN compared to silicon carbide MOSFET.
Okay. Kind of a similar question here. On slide 25, you use silicon carbide for the PFC fast switching leg. Would GaN work here also?
So it's basically the complementary question. Yeah. Of course, the GaN would work there, but as also Martin explained in the presentation, we talk about high power. especially in certain applications like onboard charger, also high operating temperatures. And in this environment, of course, silicon carbide has some competitive benefit, especially due to the better, let's say, behavior with the reference to temperature, especially on the RDS(on). The change of RDS(on) versus temperature is a little bit lower with silicon carbide compared to GaN. And that's the reason why finally SiC is, in our opinion, the best fit for this topology.
Okay. What kind of motors would benefit from the higher frequency with the lower motor temperature you showed in slide 33?
Yeah, I mean, this comes down to the phase-to-phase inductance. Like I mentioned, the motor that we tested in that slide had 10 or 20 microhenries of inductance, and that's around the same inductance you would have in a buck converter or any kind of DC-DC application. So you see that same benefit. But if you imagine designing a DC-DC converter with a power filter inductor that has 1 millihenry of inductance, then your switching frequency doesn't really matter because the inductance is so high. So there are certain types of motors, typically motors that are designed for very low speed and very high torque without much gearing involved. Those seem to have very high inductance, but this is a qualitative relationship. You can design a motor however you want, but if you go out there and on the open market and buy a motor, typically the higher speed motors are going to have lower inductances most of the time.
All right, very good. Well, we're up on the top of the hour here, so I want to thank the Infineon team for their excellent presentation and a really good Q&A session. Thanks to the audience for that too. Before we close out this All About Analog and Power live session, I'd like to announce our prize winners. Congratulations, Dale Yanni, and Carl Gansinger. We'll be in touch with you in the next week to ensure we have the information we need to send you the All About Circuits goodies. In a moment, everyone, you'll be redirected to Infineon's Summit Series microsite. I encourage you to check out the other live sessions, the keynotes, and published content for this month-long virtual event. Thank you, everyone, for attending the All About Circuits Summit.